Okay, so the intermediate value theorem can be applied to a wide variety of problems that perhaps are not immediately clear, that there are easy applications of this when you first read them, but with practice you'll learn to recognize immediately that they are about this particular theorem. So one example is this. So whenever they're asking you to show that a certain equation has a solution, probably what they're asking you is to use the intermediate value theorem. So one is to show that the equation cosine of x is equal to x has a solution in the interval 0 and pi over 2. Okay, so here they're not asking you to show that a given function attains a certain value, but that there's an equation, in this case cosine of x equals x, and you have to conclude that that equation has a solution inside a given interval. So the way to apply the intermediate value theorem is to define a function that's going to be continuous inside that interval. So here a and b are going to be given to you, 0 and pi over 2, and then applying the same steps as before. So the first thing here is we're going to define f of x as cosine of x minus x. Okay. This function here is continuous because cosine is a trigonometric function and x is a polynomial, simple polynomial. This is continuous, and when you add or subtract continuous functions, the resulting function is continuous. So that's step one. Here note that a is equal to 0 and b is equal to pi over 2. And question now is, what is the value that we're aiming for? M is equal to what? So this equation, cosine of x equals x, will have a solution if cosine of x minus x is equal to 0 at some point. Right? So if cosine of x minus x is equal to 0, then that implies that cosine x is equal to x. Just move x to the other side. And we'll have shown that this equation has a solution. So the value we're aiming for, m, here is equal to 0. Alright, so now the point to this was step 1 already. And then step 2, we must show that m, which is equal to 0, is in between f of 0 and f of pi over 2. So what about f of 0? You have cosine of 0 minus 0, and cosine of 0 is 1, so this is equal to 1, right? What about f of pi over 2? Cosine of pi over 2 minus pi over 2 is equal to, well, let's look at cosine of pi over 2. This is equal to 0 minus pi over 2. This is minus pi over 2. And this is a negative number, minus pi over 2, and 1 is a positive number, so m is clearly in between two of them. So f of pi over 2 is less than 0 and is smaller than f of 0, which is 1, you remember. So this is the second step. So we check that the value m is in between the values of f at both endpoints. And then the final step is just to say that by the intermediate value theorem, f or there is a value, there is a c, a number c in between 0 and pi over 2 such that f at c is equal to m, which is equal to 0, right? And this means here that what is f? F, remember, is cosine of x minus x. So this means that cosine of c minus c is equal to 0. Again, which we already mentioned, this implies that cosine of c is equal to z. So this implies that c is a solution to the equation. And this is what we were asked to show. That this equation here, cosine of x equals x, has a solution in between 0 and pi over 2. This is another way in which you can apply the intermediate value theorem. So when they ask you to show that the certain equation has a solution, and typically the way you do that is you move everything to one side and call that your function f. Okay, so whenever you have something that says you're told that it's you're told to solve. I mean, you're not actually asked to solve or find an explicit value for x, but you're asked to show that there's at least one solution. Then you move everything to one side, set it equal to 0, and what you have on one side, the side where all the x's appear, you call that f, and you must find a point where f is negative, a point where f is positive, and then there must be a value in between where f vanishes. So that's a very important corollary. Corollary of the intermediate value theorem, and this is how you apply it usually when you're asked to show that a given equation has a solution. So if f is continuous again on a closed interval AB, and f of A, f of B are non-zero and have opposite signs, then f has a 0 in a B. And this is exactly what we applied in the example before. Okay, so we're asked to find a 0 function. So for us, whenever we're asked to find a solution to an equation, we'll transform that problem into finding a 0 of a function. Okay, so in applications, finding zeros, no, finding solutions to an equation, not actually finding them, but showing that these solutions exist. Equation will be transformed into a problem about finding zeros of a continuous function. Okay, so this is a first remark that we make. Second one is that the at least part of the theorem is necessary. So in general, the function may not attain a value just once, unless the function is injective. So the value m may be attained multiple times. So the theorem just tells you there is at least one. It doesn't tell you that there's exactly one. So if you look at this, for instance, you can see that if you call this, say, A, and this equal to B, so that this is f of B, and this more value here is just f of A. Then if you look at this m, then m is attained at several different points inside the interval. So this could be C1, C2, C3, C4, and C5. So f of C1, C2, f of C3, f of C4, f of C5, and they're all equal to m. So the theorem just tells you that there is at least one. In this case, there are 5 points. So that's all it says. And okay, so now we see that okay, summarizing, in applications, finding solutions to an equation will be equivalent, or we will transform them into a problem about finding zeros of a continuous function. And this is also the case when finding roots of polynomials. Finding roots of a polynomial means finding zeros of the given polynomial. Okay, so this is just one type of application. And the value m may be attained, or it may not be attained multiple times inside the interval. And one final remark is the following. If f of, if you know that if f is continuous inside an interval, so a b, when m is not in between f of a and f of b, nothing can be said about the existence of an m, no, of a value of a number c in between a and b, such that f of no, such that f of c is equal to m. So both things can happen. There can be a value in between such that f of c is equal to m, or there may not be any value. So two very simple examples. So here a constant function, so f of x is just equal to 1. Then in between a and b, then there is no c such that f of c is equal to 2. And of course 2 is not between f of a and f of b, and because f of a and f of b is equal to 1. So it's not contained there. But now what about this other example? So this is sine of x. F of x is equal to sine of x, so this is 0 pi over 2. No, sorry, 0 pi and 2 pi. So f of 0 is equal to f of 2 pi, which is 0. And m equals equal 1. It's certainly not in between these values. However, f of pi over 2 is equal to 1, for example. So nothing can be said about that. So these are the three very important remarks, very important things to keep in mind. Okay, so what about some other applications, some other problems? So let's look into that. So another example. Does f of x equals 2x cubed plus 5x have the value 55 for some x in 1, 3? Explain. So for the solution, we know f is continuous. It's a polynomial. This is continuous everywhere, in particular in between 1 and 3. Now, f of 1, so this is the step 1. Now the second step. f of 1 is equal to 2 times 1 plus 5 times 1 cubed, which is 1, times 1, is equal to 7. What about f of 3? It's 2 times 3 cubed plus 5 times 3. 3 cubed is 27, so this is 54 plus 15. So that's 69. And 55 is in between f of 3 and f of 1. Remember, the f of 1 is 7, and this is 69. So this also checks out. And so the final step, step 3, is to conclude then there, so the IVT implies the existence of a value c in between 1 and 3 such that f of c is equal to 55. Okay, so the basics summarizes all the kinds of problems you may be asked about this topic. So we'll continue in the next video.